Good afternoon, everyone. My name is Mark Miller, and today I'm going to be talking about a topic used all throughout fluid mechanics known as Bernoulli's equation. So before we get into Bernoulli's equation, we need to talk about a little bit of background about streamlines. Now, streamlines are lines that are tangent to the velocity vectors throughout the flow field. And so this really describes the flow field in which fluid flows. So for example, we have this streamline drawn here, almost like a sinusoidal wave here, and we have 2 points along the streamline, point 1 and point 2. Now point 1 has a specific pressure P1, a velocity V1, and an elevation Z1, and the second point, point 2, has a specific pressure P2, a velocity V2, and an elevation Z2. Now, given some of these values, how are we able to solve for the other values throughout these equations? And the answer is going to be known as Bernoulli's equation. So before we get into Bernoulli's equation, there are certain assumptions that need to be made in order for Bernoulli's equation to be valid. We need to assume a steady flow, so the partial derivative with respect to time is equal to 0. We need to assume that the density throughout the fluid is constant, so this fluid is incompressible. We need to assume that the fluid is inviscid, also known as the viscous effects are negligible, and both of these points are along the same streamline. And if all these assumptions are met, then Bernoulli's equation is valid. Now, going into Bernoulli's equation, it's a conservation of energy equation, and here it is. We have P plus 1/2 rho V squared plus gamma Z equals constant, which equals the total pressure. So the total pressure is constant throughout the streamline. Now, let me go ahead and talk about each of these terms. So P is the static pressure at the point. So if the flow was not flowing at all, if the fluid was not flowing at all, this would be the pressure derived, or this would be the pressure measured by a manometer. Plus 1/2 rho V squared, which is 1/2 times the density times the velocity squared, and this is known as the dynamic pressure. So this is the pressure due to the fluid flowing throughout the flow field. Plus gamma Z, which is plus the specific weight times the elevation, and this is known as the hydrostatic pressure. And again, this is equal to a constant, also known as the total pressure. Now, there are various forms of Bernoulli's equation, and two of them are shown here, where the first equation, we divide the first equation by the density, and we have it equal to P over rho plus V squared over 2 plus GZ equals constant. And this is known as, another form of the equation that we might use given based off of what we're given in the problem statement. Next we have next we divide the entire equation by gamma, also known as the specific weight, and we get P over gamma plus V squared over 2G plus Z equals Bernoulli's constant. So I'm going to talk about each of these terms here. So P over gamma, which is known as the pressure head. And this is also known as the height of the fluid column necessary in order to obtain pressure P at the bottom. Plus V squared over 2G, this is known as the velocity head. So this is the height of a column, this is the height of a particle at the top of a column, which if released from rest, this would attain a velocity V. Plus Z, which is just the potential energy of a fluid particle at that point, and that all equals Bernoulli's constant. And so from the example shown earlier, where we have 2 points along the streamline, how would we solve for each of these, how would these points be related? And we have that equation shown here, where we have P1 plus 1/2 rho V1 squared plus gamma Z1 equals P2 plus 1/2 rho V2 squared plus gamma Z2. Again, this is all along a streamline, and this is the entire background necessary in order for Bernoulli's equation to be valid. So next we're going to get into an example here. And I'm going to be doing example 3.34 from the book. So given in the problem statement, streams of water from 2 tanks impinge upon each other as shown. If viscous effects are negligible and point A is a stagnation point, determine the height h. So we have a diagram of the 2 tanks here, where we have 2 points. We have point 2 and 0.1 here. And we're given that P1 here is 25 psi. And we're given P2 is open to the atmosphere, so P2 is essentially 0. We're given this height h, and this is what we need to solve for. And these two free jets here, assume these are free jets, this here, these two free jets here are impinging upon each other, and we need to calculate how far h is from the second tank. And we're given that the elevation of point A above the ground is 20 feet. And we're also given the elevation of point 1 to be 8 feet. So another assumption that we have to make here is that tank A and tank B are very large. So essentially the velocity at point 1 and the velocity at point 2 are essentially 0. Now using everything that we're given, we need to find h. And so this is a simple Bernoulli's equation problem, so let's go ahead and get into it. So here's the solution here. We start off with Bernoulli's equation. P2 over gamma plus V2 squared over 2G plus Z2 equals PA over gamma plus VA squared over 2G plus ZA. So I'm relating points 2 and point A to each other. And so this is going to come up with our first equation used to solve for h. So just a couple of things we get from this equation. P2 is equal to 0 since it's open to the atmosphere. V2 is equal to 0 since the tank is large. Z2 is equal to h plus 20 feet given in the problem statement. VA is equal to 0 because it's a stagnation point. And ZA given in the problem statement is 20 feet. So we're able to strike out all of these terms here, P2, V2, and VA. And we're given this new equation here where h plus 20 equals PA over gamma plus 20. So this goes, and both the 20s cancel, so we're given h equals PA over gamma. Next we have a second equation, which we're going to relate points 1 and point A. So PA over gamma plus VA squared over 2G plus ZA equals P1 over gamma plus V1 squared over 2G plus Z1. So assumptions that we can make from here: VA is still equal to 0 since the stagnation point. ZA equals 20 feet given in the problem statement. P1 equals 25 psi, which was also given in the problem statement. V1 equals 0 since the tank is large, and Z1 equals 8 feet, which is also given in the problem statement. So from here we're able to plug in these terms. PA over gamma plus 20 feet equals P1 over gamma plus 8 feet. So this goes to PA over gamma equals P1 over gamma minus 12 feet. And again, we know that PA over gamma equals h, so we're able to get an equation for h. H equals P1 over gamma minus 12 feet. And we know all of these terms, so we can easily solve for h right here. And so this is what we use. H equals 25 psi times 144 inches squared per feet squared, so this just makes it pounds per square foot, over gamma, which is the specific weight of water, which is 62.4 pounds per foot cubed, minus 12 feet. And this ultimately gets us 45.7 feet. And this is the height h that we needed to solve for. So again, recapping what we did, we related points 2 to point A using Bernoulli's equation. We related point 1 to point A using Bernoulli's equation. And using these two equations, we were able to solve for h. And that's ultimately the power of Bernoulli's equation, making these problems very simple. And so that's everything you need to know regarding Bernoulli's equation, including an example. And hope you all have a good day. Thank you.